Hi, this is Klaus again from electronics.unmasked. Today I will explain step by step how to map a building with thermal insulation in our Excel tool. And of course, I will demonstrate again some interesting effects on this way. We want to predict the energy savings from thermal insulation. In the last part of our step-by-step guide, we saw how to optimize the temperature control in the house to save heating energy. We also considered the contribution of the sun, waste heat from electrical devices, and even from the people living in the house. In this part, we will cover thermal insulation. This is particularly interesting because, on one hand, thermal insulation measures can actually significantly reduce energy consumption. On the other hand, the measures are always associated with effort and costs. Our tool will help you to find out which measures could really be worthwhile in your case. Of course, our tool does not replace the specialist, but you can use it to make a good estimate yourself, which does not cost anything. We will use our well-known example house with the 4 floors again, because this example contains all the scenarios that the tool can calculate. I will show you later how other houses, for example houses without a basement, or with a flat roof, can also be modeled for the energy consumption forecast. There is a lot of know-how about heat flows, temperature differences, etc. in the calculations that would otherwise be not so easy to carry out. I will link you to the earlier videos on the top right. By the way, there will be more videos for the step-by-step instructions. So stay tuned and subscribe to the channel. After we have specified the average temperature values for our local climate and the desired temperature in the house, it is now a matter of specifying the interfaces through which the exchange of heat energy can take place. So we need to measure the area of these interfaces on our house. The logic for this is quite simple. We distinguish 2 basic categories here. The first category are interfaces through which heat energy flows to the outside. Wall outside, roof outside, window outside, door outside and outside ground. The energy for heating or air conditioning flowing through these interfacing areas is practically lost, because it goes out to the environment. The second category is interfaces through which thermal energy can flow between floors in the house. These are the false ceilings in the house, for example between the attic floor and the first floor, between the first floor and the ground floor, etc. This energy practically remains in the house. What we need is now the size of these interfaces in square meters, which we then simply enter into our small matrix here. The irrelevant fields are gray and locked. And since the matrix has to be symmetrical, only the top right boxes need to be filled in. I have measured all the areas in my example house and now enter them accordingly here. In my attic floor I have 40 square meters of wall outside. So that would be this triangular area up here on the house. The first floor has 100 square meters of wall outside and so on. And yes, the basement also has a small piece of wall outside of about 20 square meters down here. The attic floor has a roof area of 130 square meters, which we enter here. The other floors have no room, so we enter 0 square meters here. However, if they had a roof, then we could put it here. We now proceed in exactly the same way with the windows and doors. We enter the corresponding areas here. Now we enter the size of the false ceilings between the floors. In our example, all false ceilings have a size of about 100 square meters, which we then enter here accordingly. Our basement has a total surface area of about 200 square meters to the ground. Here, of course, we have to add up the walls and the floor area. Now we are almost done. We just have to fill in 0 for the remaining boxes. With this, we defined that there are no boundary surfaces between the other spaces through which heat energy could flow. Next, we need to specify the thermal conductivity of our interfaces. The so-called U value in watts per Kelvin and square meter tells us how many watts of thermal energy flow through an interface, for example a wall with a temperature difference in degrees Kelvin per square meter. You can find many examples of thermally insulated walls, roofs, floors, etc. on the internet. And you will also find the U values for windows and doors. I summarized the whole range of these U values here. This gives you an overview of what is good and what is bad. On the left, we see the values that you might still find in old buildings, and on the right are the values that correspond to very good insulation. I have to mention that the insulation is not applied to the false ceilings in most cases between heated rooms, because this thermal energy remains in the house. With the little overview I gave earlier, you can now assess our example house for yourself. The outside walls are not bad, with a value of 0.7 watts per Kelvin and square meter, but they are far from good either. The same applies for the roof, windows and doors. The result is a rather poor energy efficiency index of 120.8 kilowatt hours per square meter per year. If you are now thinking about improvements, then the question is always which measures can be taken to achieve most benefit. What thickness of wall insulation to choose? How much money do you want to invest in well-insulating doors and windows? A simple measure would be the insulation of the roof or the false ceiling to the attic. But how much improvement does that bring? In the end, the measures cost money and effort, and you would just like to know in advance how much you can save afterwards. And apart from the business case, you want to minimize the impact on the environment caused by the consumption of heating energy. At this point, I would like to briefly demonstrate the effect of these U values. Our roof currently has a U value of 0.5. It is relatively easy to insulate a roof from the inside. We assume that we would achieve a value of 0.15 here. As a result, our energy efficiency index drops from 120.8 to 108.9 kilowatt hours per square meter per year. With affordable doors and windows, we would achieve a U value of 1.3. This would allow us to bring our efficiency index to 97.2. Then we improve the insulation of the false ceiling to the basement with a U value of 0.3. This relatively simple measure would bring us to 74.9. Compared to 120.8, we would already save 38% of heating energy. Now we are going to do one more step, which is probably the most expensive one. We insulate the outer walls and achieve a U value of 0.17. The energy efficiency index would then be 41.9 kilowatt per hour. Altogether would save 65% of heating energy. This does not include the savings from waste heat from electrical devices and from the sun. You could further optimize this with better insulation values and also play with your own temperature settings. With really good insulation, you get to a point where the amount of heating energy required is practically zero, since the sun and the waste heat from electrical devices is then already sufficient to heat your house. Wouldn't that be great? And that was the third part of our step-by-step user's guide. We have seen again how our tool gives immediate feedback on the energy efficiency indicators with every change. I hope you had fun. If there are any questions about the third part, please ask in the comments. I will be happy to answer. Maybe you have already started measuring your house. And then definitely stay tuned, because in the next part I will show how to map other types of houses. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.